Welcome to this chapter. This chapter is about the interaction of the different radiations with matter. The first topic is alpha rays. As you know, alpha rays are composed of alpha particles and they have a general discrete energies of 3 to 8 mega electron volts. These are discrete energies. We will see that the beta radiation will be different from this point of view. What does it mean, this energy? If we have a look at the penetration range in air, this is from 3 to 8 centimeters. That means it is very easy to memorize. So the penetration range of alpha rays in atmospheric air is about 1 centimeter per mega electron volt. So if you are about 10 centimeters away from an alpha source, then you are absolutely safe. The alpha rays will not reach your body. What does it mean, that interaction with matter? Mostly this is, the mechanism which is responsible for the energy transfer, because this is what we are interested in, is collision with the electrons. So this is the energy transfer to the electrons, described by this formula. Don't be afraid of this formula. The only thing I would like to emphasize that in this formula there are several parameters, but this is here the velocity square of the alpha particle. The velocity square is proportional to the energy of the alpha particle. The other parameters are here. This is Z, this is the atomic number. This actually for alpha particle, this is 2. This is the electron the charge of the electron. This is the mass of the electron. This is a parameter actually the distance between the electron, the smallest distance between the electron and the alpha particle. But this is the point, as I mentioned, since this is in the denominator of this formula, of this ratio, that means that the lower the energy of the alpha particle, the higher is the transferred energy to matter. I think it is very interesting. One would think at the first sight that, okay, if the energy is high, then probably the transferred energy is also high. No, it is just the other way around. The lower the energy of the alpha particle, the higher is the transferred energy to matter. So that means that alpha particles have the greatest destruction power in human tissue, and this destruction reaches its maximum just before the complete absorption. Actually, this means a few micrometers in human tissue. So alpha particles are totally absorbed in our body in a few micrometers, actually in our skin. This is a very famous experiment in which they measured the transferred energy of the alpha particles to air when the alpha particles penetration into air. You see, this is the penetration distance in centimeters. As the penetration goes on, of course, the alpha particle energy will decrease. However, as you see, the transfer energy is increasing. So this is the experimental proof of this formula. So this is really what happens. Of course, when there is hardly any more energy of the alpha particle, the transferred energy will drop to zero, of course. What does it mean? Alpha particles may be used to kill tumor cells in nuclear medicine, because the alpha particles are extremely destructive, and as you see, the penetration range is a few micrometers. So if you can target very well, the medical doctor can send the alpha emitter to the appropriate place, then the tissue can be destroyed in a very, very small vicinity. So this may be a very good tool in the hand of a medical doctor in therapy, first of all. Let's talk about beta rays. Beta rays are composed of electrons or positrons. The common energies range just from 0 to 3 mega electron volts. It is interesting why to mention 0. The reason is relatively simple, because the beta rays have a continuous energy spectrum. So it goes from 0 to a maximum energy. It has physical reason. We have no time now to discuss these details. So this is a continuous spectrum, actually because of the neutrinos, which are also emitted when beta decay occurs. For the 0 to 3 mega electron volt electrons, we have a penetration range in air from 0 to 3 meters. You see, again, it's very simple. So the penetration range for beta radiation in air is about 1 meter per mega electron volt. You remember for alpha particles it was 1 centimeter per mega electron volt. Here it is 1 meter per mega electron volt. What about the interaction with matter? Again, it is typical with electrons. And this is the formula which describes the transfer energy. Yes, I agree that this formula is a little bit more complicated than the previous one for alpha. However, the situation is very similar. And for the same reason, we can again find the velocity square of the beta particle in the denominator of this ratio. And again, the conclusion is that the lower the energy of the beta particle, the higher is the transfer energy to matter. So the same conclusion as for alpha particles. What is the difference? There is an important difference that beta particles still have a great destruction power in human tissue, but it is in the millimeter range, not the micrometer range, as in the case of the alpha particles. It is the millimeter range. Therefore, just like for alpha particles, and actually beta particles are much more frequently used for this purpose. So beta emitters or beta particles can be used to kill tumor cells in nuclear medicine. What about positrons? As I said, if the energy is high, that it doesn't matter if you have positrons or electrons. However, once the positrons are thermalized, they will react with electrons and produce annihilation gamma quanta. These annihilation gamma quanta can be used in nuclear medicine for diagnostics. We will learn later how. There's another important remark I will make. You see here that this energy transfer, so this formula for the energy transfer shows a subscript that means ionization. In other words, it is the energy transferred by collision with electrons. However, beta particles lose energy in matter not only by collisions, but also by emitting so-called Bremsstrahlung X-rays. That's a little bit tongue twister, I agree. This has little relevance to nuclear medicine. However, I can tell you that, yes, it is not important for nuclear medicine, but it is the most important for the traditional regular X-ray investigations. Whenever you go to see a doctor and an X-ray, a lung X-ray is taken, or maybe your teeth are X-rayed, in that case the medical doctor uses Bremsstrahlung X-ray. So that's what from the X-ray tube is coming and help the doctor to get an image, a very simple image of your body. Gamma rays. You may remember that there is no separate type of radioactive decay like gamma decay. Gamma rays are emitted normally after a beta decay or an alpha decay when we have an excited nucleus as the first product of the decay. And when the de-excitation occurs, then we have some gamma photons emitted. The common energy of these gamma photons ranges from 5 roughly from 5 kilo electron volt to 2.5 mega electron volts. It doesn't mean that this is the restricted range of energies for our gamma rays in general. This is the gamma energies you may expect for all the radioisotopes you may have access to, what you can purchase in the market or whatever I say. What about the penetration range in air? I have to tell you, this is not really defined. We say there is an exponential decrease in the intensity of the gamma rays when the gamma ray travels in a material. So there is no penetration range. Actually, for gamma rays, I may say that almost everything is more or less transparent. Even lead or brick or concrete, all these materials are more or less transparent. And also the human body is more or less transparent, and that is the basis of the application of gamma rays in nuclear medicine. There is a very important remark. Let me make a note. X-rays are produced, so far we have talked about X-rays only, by electron transitions or by attenuation of charged particles in a Coulomb field. This latter is the Bremsstrahlung X-ray, you may remember. However, gamma rays are always of nuclear origin, so the source of gamma rays is always the excitation of nuclei. What about the interaction with matter? Yeah, again, typically with electrons, but it is pretty complicated. There are several mechanisms. The first is the so-called Compton scattering. This, how to say, I may determine as corpuscular collision event when a fraction of the gamma energy is transferred to an electron. Okay, so this is a corpuscular event when the electron and also the photon act as a particle. In contrast, when you have the photoelectric effect, then both the gamma photon and also the electron act as a wave. So this is a resonance phenomenon, a wave phenomenon, and in this photoelectric effect, the total gamma energy is transferred to the matter, actually to a bound electron. Pair formation is relatively rare. I would say when we have too high gamma energy, then this is a so-called relativistic corpuscular phenomenon, and the electron-positron pair forms, and in this event, the total or a fraction of the gamma energy is transferred to material. It is not very relevant in nuclear medicine. The point for us is that the gamma photons emitted by incorporated radionuclides can easily escape from the body and be detected by external detectors. Therefore, they can be used for diagnostics when combined with isotope labeling of molecules with specific biochemical role. These are called radiopharmacons. We will see later how it works. Thank you very much for your attention.